Savi YouTube channel created by Sai Vidya Institute of Technology, Bangalore. The last sessions we were solving problems on Thevenin's or Norton's theorem on dependent sources. Now let us continue two more problems in this session. The problem statement is you have to obtain Thevenin's equivalent circuit across the terminals A and B. So, Thevenin's equivalent circuit means a voltage source V Thevenin in series with a resistance or Thevenin across the terminals A and B. That is, this part of the network I have to convert it into a single voltage source in series with a resistance. Now, let us find these two parameters. So, step 1, to find V Thevenin. What is V Thevenin? V Thevenin is nothing but open circuit voltage across the load terminals. So, load is not given in the problem, already open circuit is created. So, just I have to find the open circuit voltage across A and B. Suppose if the load were given in the problem, then you have to open the load to find the open circuit voltage. You have to remove the load to find the open circuit voltage. Since load is not given in the problem, already created open circuit, just I have to find the open circuit voltage across A and B. That voltage is your V Thevenin. Okay. Now, how to find the open circuit voltage? Now, voltage between A and B is Vx, which is given. You have a dependent source. So, dependent variable is Vx. This is a current source because arrow is given depending on voltage. Hence, it is a voltage dependent current source. The dependent variable must be given in the problem. Yes, it is given. If this is not given, you cannot solve the problem. So, that itself is V Thevenin in this problem, that is Vx becomes equal to V Thevenin. And how to find V Thevenin? You have to go for either mesh analysis or nodal analysis. Now, I will prefer to go either if you can take mesh analysis, we will get having one loop, you can take I1 and we can solve it. Or if you want to go by nodal analysis, then you can have this principal node and you can take this as reference node, because only one node we can take in this problem, that is principal node. To measure the voltages in any network, I need one reference node. Hence, this usually in most of the problems, the bottom line will be considered as reference node. Then what is this voltage? You can see here, this is open circuit, no current is flowing here. Okay, voltage drop across this is 0. So, voltage drop is equal to 0. Voltage drop 0 means what? It is a short circuit. Hence, voltage at this point is same as voltage at this point. Meaning is, so voltage between A and B is V Thevenin, that is equal to Vx, that is equal to Va minus Vb actually. Since Vb is nothing but this point, it is equal to 0, reference 0, therefore, V Thevenin is equal to Vx is equal to Va. So, that is, I can take the voltage of this node as Va or it is equal to Vx equal to V Thevenin. Now, let us apply KCL. Applying KCL at node A. So, applying KCL at node A, at this point, how many currents are meeting? Two currents are meeting. This is open, no current is coming here or going here in this branch. I should write algebraic sum of these two currents must be equated to 0. So, incoming current we will take negative, outgoing current we can take positive when you are writing KCL. That is what we are following from the beginning. Now, you know that current is entering here, you do not know the current is entering or leaving, you are assuming. Even though you know what you are doing in writing KCL, you are assuming that the currents are leaving the node when you are writing KCL. If you know, you are not assuming. If you do not know, you are assuming currents are leaving the node, and you are writing the KCL to any node, you are assuming that node voltage is at higher potential compared to other nodes. Now let us write KCL here. Potential difference divided by resistance gives the current here. Here you know current. So what is the KCL now? VA minus 4 divided by 2K. VA minus 4 divided by 2K. 2K means 2000. Incoming current is negative. Vx by 4000 is equal to 0. I repeat, KCL at this node. What is the current here? VA minus 4. Potential difference divided by resistance gives current. This current is positive. Why it is positive? Because outgoing current. You are assuming outgoing current positive. Incoming current is negative. Negative. What is the current? Vx by 4000. This is the equation. Now you know VA equal to Vx is equal to V Thevenin. So VA is equal to Vx is equal to V Thevenin. Correct? So that I can replace this by V Thevenin minus 4 divided by 2000 minus V Thevenin divided by 4000 is equal to 0. Now I have to simplify this. Let us take LCM here. With LCM 4000, then it becomes 2 into V Thevenin minus 4 minus V Thevenin is equal to 0. It is just LCM math, simple mathematics. So cross multiplying, we get 2 into V Thevenin minus 4 minus V Thevenin is equal to 0. Now let us simplify this. So 2 V Thevenin minus 8 minus V Thevenin is equal to 0. 2 V Thevenin minus V Thevenin is V Thevenin is equal to what? 8. Therefore, what is the open circuit voltage? Which is equal to 8 volts. I think you have followed how to find the open circuit voltage. Next, what I should find? I should find R Thevenin. Let us go for step 2. Step 2, to find R Thevenin. To find R Thevenin. What is R Thevenin? When there is a dependent source. So R Thevenin is equal to V Thevenin divided by IN. So when there is a dependent source in the network, to find R Thevenin, we make use of this simple formula. What is V Thevenin? V Thevenin is nothing but open circuit voltage. Already we found. IN is nothing but what? It is short circuit current flowing to the load terminals. So therefore, now I have to find IN. So to find IN. So what I should do? To find IN, short circuit the load terminals. First you have to short circuit the load terminals and then find the short circuit current. Okay, IN. Come back here. Which is the load terminal here? A and B. Okay, now I have to create the short circuit. Now let us create the short circuit. I have created the short circuit. Then I have to find this current, short circuit current. That is what? IN. Current flow is assumed to be from A to B when you are finding the short circuit current. Now all of you observe here. Again, I have not disturbed the network here. My intention is to find short circuit current. To find the short circuit current, you can go for either nodal analysis or mesh analysis. If you go for mesh analysis, you have two loops. This current can be taken as I1, this current can be taken as I2. So KVL cannot be applied then because the current source is common to two loops. Then you have to write one current equation because you have one current source. Then you have to take super mesh to get one more equation. Then solving both the equations, you will get the current I2 that I2 is equal to IN. That is one way of solving this problem. The other way of solving this problem directly looking to the network is, all of you observe here carefully, I have created the short circuit. Then what is the voltage across the short circuit? You know, voltage across the short circuit is 0. Therefore, what is Vx here? Vx equal to 0 because Vx is shown across the short circuit. Very important is when there is a dependent source, dependent variable must be there in the network. When you are rewriting this circuit, if you miss writing Vx, then you cannot solve this problem. Therefore, when there is a dependent source, you must see where is the dependent variable in the given network. Okay. Now, here Vx equal to 0. Why Vx equal to 0? Since voltage across the short circuit is 0. Voltage across the short circuit is 0. When Vx equal to 0, what happens to this current source? This current source value becomes 0. Okay, Vx equal to 0. Then this value becomes 0. When this current value becomes 0, what is the meaning of current is 0? Current is 0 under open circuit conditions. Therefore, I can remove this. I can create the open circuit. So, I can remove this. When I remove this, this will not exist. I can remove this. Then what is remaining? IN. We have only one loop. I can find current directly. IN here. IN is equal to what? In a single loop network, current is equal to voltage divided by total resistance in that loop. That is 4 divided by 3 plus 2, 5K. That is 5000. 5K. That is how much? 0.8 milliampere. Okay, 0.8 milliampere. You got IN now. Then my intention is to find R Thevenin. So R Thevenin is equal to V Thevenin divided by IN. So what is V Thevenin? Is equal to 8 volts divided by 0.8 milli gives what? 10 kilo ohm. So R Thevenin is equal to 10 kilo ohm. Now you got V Thevenin, you got R Thevenin. Then what is your intention? Just to write the Thevenin's equivalent circuit. Now let us write Thevenin's equivalent circuit. Now, what is Thevenin's equivalent circuit? A voltage source V Thevenin in series with a resistance R Thevenin. What is R Thevenin you got? 10K. What is V Thevenin you got? 8 volts. That's all. This is the solution for this problem. Hope all of you have followed. Let us continue one more problem on Norton's theorem. Find the current flowing through the load using Norton's theorem. So, load is given here across the terminals A and B. Your intention is to find current flowing through this load by using Norton's theorem. So, Norton's theorem means we have to convert the given network into a single current source IN in parallel with a resistance RN across the same load terminals A and B. So, Norton's theorem means you have to convert the given network into a single current source IN in parallel with a single resistance Rn across the same load terminals A and B. Then once you get this Norton's equivalent circuit, your intention may be finding current through the load. This load will be connected across this Norton's equivalent circuit. Just then by using current division rule, you can find the current flowing to the load. That is the concept of the theorem. Now what I should find first? Step 1, I have to find Norton's current. Step 2, I have to find Norton's resistance. Step 3, I have to write Norton's equivalent circuit and then connect the load across the Norton's equivalent circuit, then find the current just by using current division rule. Okay. Step 1, to find Norton's current IN. So, what is Norton's current? Norton's current is nothing but the short circuit current. Where I have to find the short circuit current? Through the load terminals. Then how to find that, what I should do? So, to find the short circuit current, remove the load and create short circuit and then find short circuit current. This is the procedure. So, remove the load. Let us remove the load. After removing the load, what I should do? Create the short circuit. Now, let us create the short circuit. Then find this short circuit current IN. This is the procedure to find the short circuit current. How to find this current? As usual, either you have to go for nodal analysis or mesh analysis to solve the currents or voltages in the given network. Now, here, if you want to solve by mesh analysis, you can take this current as I1, this current as I2, solving for I1, I2. So, I2 current gives IN. If you want to solve by nodal analysis also, you can solve. Now, what I will do here is, if you carefully observe, without going for mesh or nodal analysis, definitely you can get the current IN. All of you observe here. This resistance is connected now across the short circuit. Any element connected across the short circuit can be neglected. Why? Because always current prefers to flow through the least resistance path. So, here when the current comes like this, you have two paths here. Always current prefers to flow through this path. When current flows through this path and no current flows through this path, then this resistance of no use. Therefore, this becomes redundant, means it's of no use in the circuit. Therefore, what I can do is, when you create the short circuit, this resistance becomes redundant, hence I can remove this. Once you remove this, what happens here? What happens? Ix will never exist. When Ix is 0, what happens to this? This becomes 0. When Ix is 0, this becomes 0. Means voltage source value becomes 0. When voltage source 0 means what? Voltage is 0 under short circuit condition. Therefore, this can be replaced by short circuit. This can be replaced by short circuit. Then what happens? We will get only one loop. So, what is the current now? I want this current. So, it becomes a single loop network, and I can write directly the short circuit current IN is equal to what? That is 12 by 6000. 12 by 6000 is your current IN. This is how simple to find IN without going for mesh or nodal analysis. If you know this concept of neglecting the elements, or when we have to consider the elements to be redundant in the network. So, IN is equal to 2 milliampere. This is called the short circuit current for this network. Then what I should find? Step 2, I have to find the resistance. What resistance? Norton's resistance. To find the Norton's resistance, again let us rewrite this circuit. Let us rewrite the circuit once again. Let us see and analyze how to find the resistance. So, this is your original network. Now, what is my step 2? Step 2 is to find Norton's resistance. to find the Norton's resistance. Now, what is the procedure to find Norton's resistance? Always when you are finding the resistance, you have to look into the open circuited load terminals only. Okay. So, and you have a dependent source. When you are having a dependent source, what is Norton's resistance? Is equal to V Thevenin by IN. So, whether you are finding Norton's resistance or Thevenin's resistance, the procedure is same. What is V Thevenin? V Thevenin is nothing but open circuit voltage. What is IN means? IN means short circuit current. So, already we got the short circuit current. Now, my intention is to find V Thevenin. V Thevenin is nothing but what? Open circuit voltage. Now, let us find to find V Thevenin. V Thevenin, what is the procedure? Remove the load, create the open circuit and find open circuit voltage. So, remove the load and create the open circuit. Create the open circuit and then find open circuit voltage. This is the procedure. Okay. IN, just I will write it here for my reference later. It is required. Let us write here. Okay. Now, open circuit voltage. So, remove the load. Remove the load, create the open circuit and find this voltage, that is called V Thevenin. Now, this voltage I can find either by using nodal analysis or mesh analysis. I will go for just mesh analysis for this. Let this current be mesh current I1, apply KVL. So, definitely you can apply KVL for this loop because you do not have any current source, both are voltage sources. You have a dependent source. So, this symbol represents dependent source, polarity represents voltage source depending on current, hence it is a current dependent voltage source. The dependent variable must be given in the problem. Yes, it is given here. Okay. Apply KVL now. 6000 I1 plus 1000 I1 is equal to what? Is equal to, or moving clockwise, negative to positive is positive 12, positive to negative is negative 2000 Ix. Okay. Where is Ix now? I have to replace Ix by the loop current when you are solving by mesh analysis. So, dependent variable must be replaced by mesh currents or loop currents if you are solving by loop analysis. So, what is Ix in terms of loop current? Current flowing to 1000 ohms is Ix. Loop current flowing to 1000 ohms is I1. Direction is also matching. Hence, I can write Ix equal to I1. So, Ix is equal to what? Capital I1. Then what happens here? So, 7000 I1 is equal to 12 minus 2000 I1. Take left hand side. So, 9000 I1 is equal to 12. So, I1 is equal to what? 12 by 9000. This is what? Your I1. Now, calculate what is I1 value. So, I1 is equal to 1.333 ampere. That is what I1. Now, what is my intention? My intention is to find V Thevenin. So, what is V Thevenin? Is equal to voltage between A and B. What is voltage between A and B? Voltage between A and B is same as voltage across 1000 ohms. Correct? Therefore, I can write this voltage is equal to 1000 into I1. 1000 into I1. That is what? V Thevenin. 1000 into I1. Okay. So, this is how much it is, not I think amps, it is milliampere. Okay. This is milliampere. Now, 1000 into what is this? 1.33 milli. Okay. That gives V Thevenin. So, if you get this V Thevenin, we get V Thevenin is equal to 1.333 volts. Okay. So 1000 into I1, that gives 1.333 volts. So that is how to find Thevenin and IN. Once you get these two parameters, definitely I can find Rn substituting here. Now let us find this value now. So Rn is equal to Thevenin by N. What is Thevenin? 1.333. IN is what? 2 milliampere. If you substitute this, you will get the value 666.5 ohms. Check the answer. Now this is what Rn. Now you got Thevenin and that is resistance and also IN. Next step 3. Write Norton's equivalent and connect the load across it. Norton's equivalent is nothing but a current source in parallel with a resistance. So IN in parallel with Rn. You know IN, you know Rn. Now connect the load across it. What is the load? I have removed the load in the first step, need to be connected in the last step. So load. What is the load value given? 667 ohms. Okay. My intention is to find current flow into this load. Now always in the Norton's equivalent circuit, to find the current, we can go for current division rule. So this current I want to find, that is what load current is equal to what? Is equal to, the two resistances are in parallel, you know total current. I can find current in this branch using current division rule. IL is equal to opposite resistance divided by sum of these two resistances into what? The total current entering into the parallel branch. Now substitute the values here, find the load current here. Find the load current. You will get around 1 milliampere. Why 1 milliampere? What is IN here? You have 2 milliampere. Okay, you have 2 milliampere. What is this value? 667. What is this value? Approximately 667. Approximately 667. So whenever two resistances are parallel and both are of equal value, the total current divides equally in these two resistances. So you are getting total of 2 milliampere. So here 1 milliampere, here when 1 milliampere will divide, so that you are getting 1 milliampere. This is how to solve this problem by Norton's theorem. Thank you for watching.